This session, we have 4 papers. And the first paper will be given by Ms. Zhang from the Nanyang Technological University, Singapore. Okay. Are you ready? Okay, please, Ms. Zhang.
Good afternoon, dear professors and researchers. I'm Betty from Nanyang Technological University, Singapore. It's my great honor to attend this OFSIS2017 conference, and I have learned a lot from you in these 2 days. Today, let me introduce our research on the abnormal noise-like pulse fiber laser for disruptive sensing applications. My presentation will be divided into 5 parts. Firstly, I will introduce some research background on noise-like pulses. After that, I will introduce our design of the system. And the third and fourth part include the theoretical modeling and experimental results. At last, I will give you a conclusion. Noise-like pulses have drawn much attention because it can offer low temporal coherence, smooth and broader spectrum, and high brightness. Owing to these merits, NLPs are widely applied in many optical sensing applications, such as hybrid interrogation of high-count, low-reflectivity fiber graduating arrays and many other fiber optical sensing systems. Noise-like pulses are usually observed when the pump of the laser is very strong. It has lots of fine structures which are different at each round trip in the time domain. And it always has a very narrow coherent spike on top of the autocorrelation trace. Although it has many random fine structures, the whole structure still stand together without any walking off, and it combined as one pulse with relatively wide envelope. In the spectrum domain, it also has plenty of fan structures, and it is usually generated by introducing reverse saturable absorption. The research on NLP can be dated back to 1997 when Dr. Horace reported this time-dependent intensity and AC trace with peak-to-shoulder ratio of 2. It has many advantages over traditional short pulses, such as higher pulse energy, high intensity, up to 50% higher average power, and it can provide more stable femtosecond narrow pulse even after passing through a very long dispersive medium. Most importantly, it provides very broad and smooth spectrum, thus it's very useful for sensing applications. It has drawn much attention in the past 10 years. However, all the peak-to-shoulder ratio reported in this literature are still fixed to 2. So we are wondering whether we can change this value to a different value so that it can be applicable for a larger range of sensing applications. And we have successfully achieved this change by using our experimental design. To design the system, let's first look at the mechanism. So self-phase modulation creates the positive frequency chirp, which can counterbalance the negative frequency chirp introduced by the dispersion effect in the anomalous cavity dispersion region. And when the peak power is very strong, the SPM can create the solitone even without the mode locker. But because of the peak power limiting effect of the cavity, multi-solitones will be formed. Thus, the laser emission is actually a combined effect of solitone collapse and the positive cavity feedback in the laser. Depending on the different linear cavity phase delay, the laser could be switched between 2 regions. One is the solitone operation, and the other is the noise-like pulse emission. So when the linear phase delay bias is very small, and when we first increase the pump power, the laser peak power will be increased and the pulse width will be decreased at the same time. However, after reaching a threshold, this phenomenon will stop. And after that, the quick solitone will be, new solitone will be quickly formed through the solitone shaping of the weak background pulses. And eventually, a multiple solitone state will be obtained. The larger the laser gain, and the more solitons will be formed in the cavity. Well, on the contrast, when the linear cavity phase delay bias is very large, for example, at 1.8 radians, we cannot obtain very stable soliton operation. Instead, the soliton will quickly die out if the laser gain is smaller than the dynamic loss, and the soliton peak power will increase if the laser gain is larger than the dynamic loss. So when the peak power is very large, the soliton will be broken into two solitons with weak peak power and broader pulse width. In a nutshell, there are two mechanisms we can obtain noise-like pulses. One is the soliton shaping of the unstable waves, and another is the very famous pulse splitting. Based on this mechanism, we have designed our urban doped fiber laser system. It's a mode locking system based on nonlinear polarization rotation, which works as artificial saturable absorber. One of the polarization controller consists of two quarter-wave plates, and the other one consists of two quarter-wave plates and one half-wave plate. As we increase the pump power from 300 milliwatt to 500 milliwatt, we can see that the auto-prediction trace changes accordingly. We can see that the noise-like pulses inside one envelope do not follow the normal distribution, and what's more important, the peak-to-shoulder ratio is not 2, which is the value for the convention noise-like pulse. And in the spectrum domain, it also changes as we increase the pump power. Specifically, the peak-to-shoulder ratio decreases from 1.558 to 1.436, which indicates that the smaller ratio of the peak power to the random pulse total power. And the spectrum width also increases as we increase the pump power. From these two figures, we can see that the optical spectrum, optical pulse energy, and pulse distribution in our laser cavity can all be tuned with the control of our pump power. To verify our experiment result, we have carried out numerical modeling, which is based on the nonlinear Schrödinger equation, which governs the propagation of optical pulse in nonlinear dispersive fibers. We use split-step Fourier method to solve this equation. The basic idea of this method is to use small steps to get a solution and to treat the linear steps and nonlinear steps separately. Linear steps and nonlinear steps are established in frequency domain and time domain respectively. But to switch between these two domains, we need to carry out the Fourier transform back and forth. This is the whole equation used in our modeling, and we have considered second and third order dispersion effect and nonlinear effect. So this is our simulation results. We can see that when the pump power is very low, it's below the threshold, there's no pulse splitting happen. But as we increase the pump power, noise-like pulses are generated by the passive mode lock fiber laser. And we can see the characterized random phase structures. This is evolution results from different angles of the simulation. Have a look at the first few round trips and the last few round trips. Here is round 199, here's round 1. We can see clearly the evolution of the noise-like pulses in the simulation. This is the simulation results out of correlation traces, and compared with that we got in the experiment, we can see these two results are very similar to each other, which means our simulation results verified our experiment results successfully. And here the green curve is from the simulation results, the blue curve is the experiment results. We can see that the trend is correct, but, and the precision can be further increased if we can further tuning the parameters in the simulation. And if we can increase the simulation window and the number of round trips. Besides the evolution of noise-like pulses, we have also simulated different kinds of noise-like pulse input, including Gaussian noise-like input with the same mean but different variance changes, and parabolic NLP, Lorentz ALP, sec NLP, and sec square NLP. From this figure, we can see that as the variance increases, the peak-to-shoulder ratio also increases, which can be intuitively explained because if the variance is large, that means the larger deviation from the mean. This also introduces a sharper spike on the autocorrelation trace. Now we come to the conclusion. We have successfully built up an urban dope mode blocking system, creating abnormal noise-like pulses, which can be used for disruptive sensing applications. The optical spectrum, pulse energy, and pulse distribution in the fiber laser cavity can all be tuned by varying the pump power. And we have achieved a special and tunable peak-to-shoulder ratio in the autocorrelation trace. We have using numerical modeling to reconstruct the possible pulse distributions. And our noise-like pulses can provide extra flexibility in a variety of applications, covering fiber grating interrogation and other optical sensing systems. That's all from my presentation. Thank you very much for your attention. If you have any questions, please do not hesitate to drop me an email. Thank you.
Thank you. We have time for a question. Any question? Okay.